This video, we're going to prove a fairly interesting fact. Let G be a group of real numbers under addition, and let N be a subgroup consisting of all the integers. So N is a subset of G. In fact, it's a subgroup. Now we want to prove that this set is isomorphic to the group of all complex numbers of absolute value 1 under multiplication. Let's call that set, I don't know why I wrote C, but let's call it complex 1. Now what does it mean to be the absolute value is 1? Well, recall that the absolute value of a complex number is, remember, A and B are real. You square A, you square B, you add them up, and you take the square root. Now, we want this to be 1. Well, the only number you take the square root of to get 1 is 1. That is basically, we want that to be 1. And I think, what can I do to guarantee that that's 1? Then I start thinking, if you have e to the I theta, this is cosine theta plus I sine theta. And the absolute value, well, that's this squared plus that squared. But that's 1. That's 1. We have the square root of 1, which is 1. So I'm going to map things to this. Okay, so another thing is, they want me to show that this quotient group is isomorphic to this. Generally, you prove this as follows. Show that there's an isomorphism, I meant to say homomorphism, call it phi, that goes from G to C1. Then show that the kernel of phi, in our case, is not K, I meant to write N. Now, whenever you have these two statements, that implies that G mod N, if you take G and you mod it with the kernel, it's isomorphic to C1. That's all you have to do, is find an isomorphism and find the kernel and pray in this case that the kernel is N. Alright, so let us do that. So we're going to define phi from the reals to C1 by phi of a real number is going to be e to the I times 2 pi times x. It's always going to be I times 2 pi times x. Okay, let us first show that this is a homomorphism. So pick two elements in R. Let x and y be in R. Now phi of x plus y. Remember, R is real numbers under addition. This is equal to e to the I times 2 pi times x plus y. But that's equal to e to the I times 2 pi x times e to the I times 2 pi y. And times is okay because this other group is under multiplication. And we are multiplying. And what we have here is this here is our phi of x times phi of y. So let's see. I showed this is equal to this. This implies that mapping is a homomorphism. Now we have that we have the mapping. So I want to show that the kernel is simply the integers. Okay. So I claim that the kernel of, not H, excuse me, the kernel of phi is equal to the integers under addition. And they use the letter n. Okay, so this is the set, this is the set. Have to show containments in both ways. So let X be in the kernel of phi. Now, first, maybe we should talk about what is the identity element. Phi goes from R to the complex 1. What's the identity element in here? Well, if you have A plus BI, which is a complex number, what can you multiply it by? What complex number do you multiply it by to get back the same number? And the answer is 1. 1 plus 0i. So 1 is the identity element. Okay. So let X be in the kernel. On one hand, phi of X is equal to e to the I times 2 pi times X. But this is supposed to equal 1. That is cosine of 2 pi X plus I times sine 2 pi X is equal to 1. Okay. Now, to get 1, we want that to be 1 and that to be 0. But that implies that 2 pi X, well, let's look at their cosine graph. At 0 pi, it's 1. At 2 pi, it's 1. At 4 pi, it's 1. At 6 pi, it's 1. At negative 2 pi is 1. At negative 4 pi is 1. That implies that this is equal to 2 pi k, where k is in z. That implies that x is in z. That implies that x is in n. So I took something in the kernel and I showed that it's in n. So what we have is that the kernel of phi is a subset of n. Now we have to work the other way around. Let X be in n. Okay. Phi of X. Well, okay, I'll use X for an integer. Remember, this is the set of integers. Phi of X is e to the I 2 pi times X. But that equals to cosine of 2 pi times an integer plus I times the sine of 2 pi times an integer. So this is 1, and if you look at the sine graph, at no multiples of pi, this is even multiples of pi, and no multiples of pi is it 1. At 0 pi it's 0, at 1 pi it's 0, at 2 pi it's 0, 3 pi, 4 pi, 5 pi, negative pi, negative 2 pi, negative 3 pi. This is always 0. So that's 1. That implies that X is an element of the kernel of phi. That implies that n, I started off with x and n, and I concluded that x is in there. So x is a subset, n is a subset of the kernel of phi. Let's call this double star, and let's come right here and call that star. Well, I have the containments in both directions. By star and double star, that implies, well, and double star, that implies that the kernel of phi is n. Now, we know that G is a homomorphism from G to C1. And the kernel of that homomorphism is n. That means if we mod G by n, it is isomorphic to C1. And that completes the proof.